Okay, first of all, I haven't been to Costco, so it's okay. And if somebody has a sheet of paper, scratch paper, we can do a sign on the sheet. So let's go on with what we were talking about. So the first thing we were talking about was making operators self-adjoint. So suppose we start with just a generic differential operator, well, for an ordinary differential equation, second order. So that's what I'm talking about. Some generic second order ordinary differential operator. And what we want to do is we want to convert it into something that's formally self-adjoint, which is to say minus d by dx of p d by dx, pb, p of x, of course, plus q. And another way of writing this is minus p d2 dx squared minus p prime d dx plus q. So we want to turn L0 into that. The first thing we do is we turn L0 into L1, which is just minus L0 over H2. And so that gives us minus p2 dx squared minus h1 over h2 ddx minus h0 over h2. Is there a question? No. Okay. By the way, there's a very good colloquium tomorrow at 3:30, Dane Smith Hall, 125. The speaker is Wick Haxton, who's been a leader for 3 decades in nuclear physics, particle physics, and more recently condensed matter physics. And he's quite a good lecturer. These colloquia are an important part of your education. And one reason I have been opposed to the preliminary exam for 35 years is, or the qualifying exam, whatever you call it, is that it focuses students' attention on undergraduate physics rather than on topics of current interest, which you're exposed to in the colloquia and seminars. All right, anyway, how are we going to fix this? Well, what we do is, comparing these two, we see what P prime would be. Namely, P prime is H1 over H2, and, well, actually, I don't know, I shouldn't have said that. That was a spontaneous mistake. So let's say what we actually do is we define p of x as an exponential. It's an exponential of an integral up to x of h1 of, let us say, y over h2 of y dy. And if you want, you can put in the lower limit here. The lower limit corresponds to an overall constant. So if you want, you can put in x0 there. Then what you do is you define L as P of xL1. And now this is minus e to this integral up to x of h1 over h2 dy. And the rest of it is L1, which is p2 dx squared minus h1 over h2 d by dx minus h0 over h2. Well, there, that. And now you can see that this is the same thing as minus d by dx of e to the integral, let us say x0 to x, h1 over h2 dy ddx minus e to this integral h1 over h2 dy h0 over h2. Okay, so that's a self-adjoint form. What you see here is that if the d by dx hits this d by dx, you just get the pre-factor times that. If the d by dx hits the exponential, that brings down h1 over h2, and you still have the exponential. Finally, this exponential hits this, and you get this last term. And I see I've also got a mistake here. There's no minus sign here. And these minus signs came from these three minus signs. And so, in fact, there's a minus sign there. I hope there's one here. Yeah, I just pulled out the minus sign. Okay. Anyway, so that's the way one does it. So now this is of the form minus d by dx, p d by dx plus q. And so what's q? Q of x is minus p of x times h0 of x over h2 of x. And p of x is this, exponential. There's a sign-in sheet somewhere. I'm just wondering, I hope everybody in this room has sent me an email about the final exam. And my preferred email is the Gmail, but to save typing, that's a short email address. Might even get to me. Okay, so what we do then to convert L0 to L is actually kind of simple. It's that L is equal to rho times L0, where rho is minus t over h2, which is to say minus an integral from some x0 to x. This Crayola chalk sucks. By the way, does anybody know a good place to buy big, thick pieces of chalk of decent quality?
Michael's.
Crayola's not the right place.
Michael's? Maybe?
Well, it's worth a try. Thank you. See how much better this chalk is. The image and so forth. Okay. Oh, hold on. And then I have to divide by h2. Okay, so that's what one does. One multiplies it by rho. And so now let's look at the solutions of this differential equation. If we're talking about just the homogeneous version, well, this implies that rho L0U will be 0, or LU will be 0. So those have the form of the same solutions. On the other hand, if we're looking at an eigenvalue equation, then in terms of L0, it looks like this. And in terms of L, we then have rho L0U equals rho lambda U, or LU equals, how did I write it? Lambda rho U. So this is an eigenvalue equation with a weight function, and this is the, so to speak, the best kind of eigenvalue equation to study. It differs from the naive one just by the fact that it does have a weight function. In quantum mechanics class, the weight function often sneaks in and without any ceremony. But this is the thing to focus on, and this is associated with the names of two mathematicians, Sturm and Liouville. Sturm sounds German, but he was actually French. And Liouville, I think, was English. Anyway, this is called a Sturm-Liouville differential equation. And this rho, I called it a weight function. On the other hand, H2 is often negative, and consequently, rho is typically positive, which you'd expect for a weight function. Okay, so on Tuesday, I think it was, we talked about wronskians, and what we said then was we had a differential equation like this. And we said, well, the wronskian is one solution times the derivative of the other minus the thing backwards, like that. And we saw that this wronskian was the wronskian at some point times an exponential x0 to x of, let us say, a minus p of x prime dx prime, where that's the p, capital P. Now, when we have an operator in formally self-adjoint form, what we can see is that the differential equation is minus p y prime plus qy, which is minus p y double prime minus p prime y prime plus q y, say equals 0 is the equation. And so by comparing these two equations, you see that big P, capital P, is P prime over P. So big P of x is P prime of x over P of x. And so this wronskian for a self-adjoint differential operator, formally self-adjoint, is e to the minus x0 to x. And now this is P prime of x prime over P of x prime dx prime. But that is just W of x0 times e to the minus integral x0 to x d log p. In fact, it's just d log p. And so this is w of x0 e to the minus log p of x plus log p of x0. And so that is w of x0 p of x0 over p of x. Okay, so what that means is that, see, that's one of the advantages of writing things in self-adjoint form. Instead of having the wronskian be some exponential of something that appeared in the differential equation, the wronskian is just a thing that appeared in the differential equation but in the denominator. That's much more useful. That's why people like self-adjoint forms. One of the many, many reasons. And we learned, I think Tuesday or maybe Thursday of last week, that if you used the method of Frobenius and Fuchs's theorem to find one solution of a differential equation by expanding, say, in power series about some singular regular point or regular singular point, you get at least one solution. And then we saw that the Wronski method got us a second solution, which is the first solution times an integral up to x of the Wronskian over the square of the first solution dx prime. And if you want, you can make that a definite integral. And so this is fine, and we talked about how useful that was. That gets you a second solution. But when the differential equation is in self-adjoint form, then the Wronskian is very simple. And so what we get, let's see, did I leave out anything there? No, that's right, okay. So, because the Wronskian is simple, what we have here is w of x0 integral from x0 to x, and I should have pulled out a p of x0. Let me do that too. So it's p of x prime y1 squared of x prime dx prime. So that's a much simpler and direct answer. The second solution is the first solution times a constant, of course, arbitrary. Then the business end is this integral over x prime up to x. And since this is a linear homogeneous equation, we don't really care about the overall constants. And a quick example is if you take, let us go to Legendre's equation. The very simplest solution is p of x equal to 1. That's actually the zeroth order Legendre polynomial. If you then go through this procedure, you have that p of x is 1 minus x squared, and so y2 then would be, since the first solution is just 1, it's some constant times an integral dx prime over 1 minus x prime squared, period. That's the end of it. And that turns out to be a half log of 1 plus x over 1 minus x. And so then we learned something from this, namely that the Legendre polynomials, of course, are perfectly regular on the interval minus 1 to 1. They're just polynomials. This thing, on the other hand, blows up at plus and minus 1. It's a log, so it's not a nuclear explosion, but it still goes to infinity. Okay, one of the things that that puzzled me a little bit, well, I guess it did, is that we talk about these self-adjoint differential operators and so forth as quadratic expressions, and yet in quantum mechanics we often have things like P and angular momentum and angular momentum represented as differential operators, and we say, oh, these things are Hermitian or self-adjoint. And so what I want to show you is that you can take, you can make a, suppose we have a first order differential operator. L is u d by dx plus v. So I want to say, well, I want to examine what do u and v have to be in order for L to be, let us say, formally self-adjoint. Well, what we would want would be an integral chi star L psi dx, which we would want that to be L dagger, in fact it is L dagger on chi star psi dx, and we would want that to be L on chi star psi dx. In other words, if L dagger is L, then this is what we would have. And here I'm talking about an integral from A to B on some interval. All right. So if we do this, then what we have is A to B chi star, and this is u psi prime plus v psi dx. Okay, well, you have a mathematician with nothing to do, he integrates by parts. So what we have here is integral A to B, and this is minus chi star u prime plus chi star v, all that times psi dx, and then the boundary terms, which is chi star u psi ab. Now we just sort of rearrange terms here. Integral A to B minus chi u star, so I'm doing the double stars essentially. Okay, so in other words, the star hits this and converts it into that. The star hits this and converts it into that. Okay. And now we just reassemble terms slightly here. We go AB minus U star chi prime plus V star minus U star prime, prime meaning d by dx, of course, chi star psi dx plus, again, the same term, chi star u psi AB. Okay, we want that to be this. In other words, we want that to be integral A to B L chi. Good. Okay. L chi star psi dx. All right. What do we need for that to be true? Well, first of all, we need this to vanish. So we need chi star u psi AB to vanish. And we need this to work. So this thing here is integral A to B L chi. Well, L was u chi prime plus V star psi dx. So what we need is the coefficient of chi prime is, in one case it's minus u star, and in the other case it's u. And then the coefficient of chi, whoops, there's a chi here. The coefficient of chi in both cases, in one case it's v star minus u star prime, and over here it's just v. So these are the three conditions that we need for this to be a self-adjoint differential operator. And well, one can write L in the form of I R of x d by dx plus S of x plus I over 2 R prime of x. And this differential operator can satisfy these conditions as long as R and S are real. And I've thrown in the I's in order to make more connection with quantum mechanics. The examples are P, of course, is H bar over I, d by dx, and that's the case. R a constant, this is the case. R is equal to minus H bar. This term vanishes, and S is equal to 0. So this is a very, very simple example. What is this? Yes? Of course. Well, what's the question? I mean... All right, buy fruity snacks if you're at Costco. Okay, sorry about that. Another example of a of this is angular momentum. I thought it was on the same page. Its Li is epsilon ijk xj pk, where this is, that's piece of 1, say. In general, pk is just a derivative with respect to xk. We're summing over j and k from 1 to 3. This is Levi-Chitty totally antisymmetric. And this satisfies this with this being h bar over I epsilon ijk xj partial xk. So that's the form. You can verify that this satisfies those rules. Another example that works is the gradient in a magnetic field. Then it's h bar over I gradient minus electric charge times vector potential. So this is another, this is effectively a covariant derivative, so we can write it as a capital T. You can verify that that satisfies these rules, so it's a formally self-adjoint first-order differential operator. All right, let me get another piece of chalk and a sip of water for coffee. So any questions, even though I don't have any candy? All right, so let's look at a variational problem that's constrained. Constrained in that we want the weight function, the eigenfunction to be normalized, which is what we normally do in quantum mechanics. So let's say we want to minimize the energy, but obviously we could minimize the energy just setting the wave function equal to 0. That would get it pretty low. So instead, we want to require that the wave function be normalized, and under those conditions, minimize the energy. And so let's consider a functional E of u. So this is similar to what we've done in the principle of stationary action and so forth. D of x, u prime, prime meaning d by dx, squared plus q of x, u squared of x dx. So this is the if you want, the energy that one minimizes subject to u being normalized, and we'll see that that generates the Sturm-Liouville eigenvalue equation. So we're going to define a normalization as a to b rho of x, u squared of x dx. And so what we want is we want to have this equal to 1 and minimize e. And what we do is we use the Lagrange multiplier. And unfortunately in my notes I used e for both things, but I guess you'll let me get rid of that. So this is integral p u prime squared plus q u squared dx minus lambda times integral rho u squared dx minus 1 ab. Okay, so what we now do, we now regard this as something to be minimized, and there are no conditions. We minimize with respect to lambda and u. And when we do the change in E, well, that's going to be A to B, and it's going to be P 2u prime change in u prime plus 2q u change in u dx minus lambda rho 2u change in u, and I guess we should say all of that integrated dx. And of course, the change in u prime is the same thing as the change in u differentiated, and we then integrate by parts, and so what we get is that this, and let's toss out this factor of 2, and so we get a half delta E is then an integral A to B P u prime change in u differentiated minus P pu prime prime change in u plus q minus lambda rho u change in u dx. And so altogether then, apart from the condition is 0, is this, and if you want, I'll keep the 1/2. Anyway, this is integral a to b minus pu prime prime plus q minus lambda rho u variation of u dx plus pu prime du ab. Okay, so we've got two choices here. We can say that we want, if we want E to be stationary, or either one, E to be stationary with respect to all tiny changes in U, including at the endpoints, then what we have is 0 is minus pu prime prime plus q minus lambda rho u equals 0, and what are called natural boundary conditions. Notice this is just a difference, but the variation in u at the two endpoints is independent. So if we want this thing to be 0 for all small changes, then we get both of these conditions, which are called natural boundary conditions. And we get this thing, which is the Sturm-Liouville equation, namely Lu understood as minus pu prime prime plus qu is equal to lambda rho u. So this Lagrange multiplier has turned into an eigenvalue, and the differential equation is in Sturm, is formally self-adjoint. If we only required E to vanish for variations that vanish at the endpoints, then all we would get would be the Sturm-Liouville equation without the boundary conditions. So you might ask, well, what is this lambda? And we can find out what lambda is by doing this. Lambda is an integral from, or lambda times rho u squared dx. So let's see how, let me just, we're going to have, I'm going to assume that we have, that the function u satisfies, makes this thing here vanish. So it satisfies the boundary conditions. And then because it's a solution of the differential equation, Lu is this equals that, this is also u Lu dx. And that then, in other words, Lu is lambda rho u, and so this equation is true. And now this is integral a to b, this u, and now we have minus pu prime prime plus qu dx, and this integrates to a to b pu prime squared plus qu squared dx, plus the boundary term that we've assumed is 0 because we assume that that U satisfies these boundary conditions, and consequently this is equal to E of U, and this is equal to N of U. So this equation is lambda N of U is equal to E of U. So this lambda is the ratio of the thing we minimized divided by the norm, and where we could say, well, you just scale the function to make the norm unity, and then lambda is just the energy. Okay, I think maybe in as much as we want to fit Legendre polynomials and Bessel functions into the course, I think I'm going to skip the rest of this derivation, which just goes to show a couple of things. Namely, if we take this ratio, E of U over N of U, we can ask two questions. Is the function E of U that minimizes this a solution of the Sturm-Liouville equation, this thing? The answer is yes. And what is the minimum value of the ratio? Well, it's the lowest eigenvalue of the Sturm-Liouville equation. So, in other words, if we look at this Sturm-Liouville equation, what we've got is this will work only for certain values, lambda. For other values, if you did the method of Frobenius, you'd get something that was non-normalizable. So, let's see, I lost my train of thought there. Okay, so we have, in other words, only for certain lambdas will there be a solution here that is normalizable. And these there'll be a least eigenvalue. The least eigenvalue is the one that minimizes this ratio. You can then say, okay, that the function that minimizes this ratio is U, and it's the eigenfunction for the least eigenvalue. Suppose you look now at minimizing this ratio with respect to functions that are orthogonal to the first eigenfunction. Then what happens is you find that the function that minimizes this ratio being orthogonal to the first one is the second eigenfunction, and it would be the eigenfunction for the next, the second smallest eigenvalue. All right, so that's basically how this works. And here there's something that is surprising here, and it is, if you continue in this way, what you find typically in the Sturm-Liouville problems that occur in physics, you find that these lambdas, lambda 1, lambda 2, and so forth, you find that the limit n goes to infinity of lambda n is infinite. That is to say, the eigenvalues might start out negative, but eventually they go to infinity. An example of the harmonic oscillator eigenvalues, En is h bar omega n plus a half. Well, for n equals 0, it's h bar omega over 2, but as n goes to infinity, the eigenvalues go to infinity. And the same thing is true, let's see, I've got here the infinite square. Well, do you want me to do any of these examples? There are 3 examples. I could do one of them if you want, or we could skip all 3. The examples are the infinite square roll, the harmonic oscillator, and Bessel systems. Okay, somebody shout. Skip 3, do 1, what?
Can we do the Bessel systems?
You want the hardest one? Really?
Well, because the other two we've already done.
You mean you've already seen the others in class?
Yeah.
All right. If I had candy, I'd give you one. All right, so let's do the Bessel system, which is actually a good choice. E of u is an integral from 0 to 1 x u prime squared of x plus n squared over x u squared of x dx, where n is an integer, n equals 0, 1, 2, and so forth. Okay, we want to minimize this over the space of twice differentiable functions. In other words, the domain is twice differential functions that differentiable functions such that n of u, which is integral 0 to 1 of x u squared of x dx, should be 1. Okay, so that's the constraint for this system. And satisfy boundary conditions. The boundary conditions are u of 0 is 0 for n greater than 0, and u is... All right, I think there may be a typo here. Sorry. I thought this was a subscript. Right, okay, so u of 0 is 0 for n greater than 0, and u at 1, because we're interested in the interval 0 to 1, u of 1 vanishes. So they all vanish at 1. And all of them vanish at 0 except for the case where n is 0. And you see why n is 0 is singled out, because if n is 0, this singular term goes away. All right, so we use a Lagrange multiplier, and what one finds is that the differential equation is Lu is minus xu prime prime plus n squared over x u equals lambda xu. So the weight function is obviously x, rho is x. And one can see that the eigenvalues are all positive, and in fact, these eigenvalues are of this form. Lambda n, that's this n. So n is fixed. In other words, n tells you what Bessel system you're talking about. For a given value of n, you have then various eigenvalues. L sub nm, we're going to call k squared sub nm. And if we change variables, oh, this is terrible notation, because I'm changing variables to rho equal to knm x. So this rho is not the weight function. This is just, so I should really not do that. I should use a different symbol. Anyway, what one then gets is the following differential equation. You set un of x equal to jn of rho, and then the equation is d2jn d rho squared, jn of rho in other words, plus 1 over rho djn d rho plus 1 minus n squared over rho squared jn equals 0. So that's Bessel's equation. And the eigenvalues then are determined by this condition, which is that Jn of k and m should vanish. That is to say, remember, rho is k and m times x. At x equal to 1, this should vanish.
Why are there two indices?
Why what?
Why are there two indices now? Why is there an in and an in? Where did the in
It's
come from?
because n characterizes the differential equation.
Okay.
M characterizes the eigenvalue.
Okay.
And these then are the zeros of the Bessel function, and the eigenvalues are the squares of the zeros of the Bessel function. And a friend of mine, David Waxman, once told me that during the Second World War, and possibly even during the 1930s, the zeros of the Bessel functions were state secrets of the British government. That's impossible for us to imagine because, well, we can just use MATLAB or Mathematica or Google to find them, but in the 40s that was the case, yeah.
Oh, like what were they used for in the war?
Well,
Like,
artillery, submarines, I mean, anytime you have cylindrical symmetry, you're stuck with a Bessel function. So think torpedoes, cannons, aircraft, fuselage is kind of a cylinder. I don't know. I'm not, I've never worked in the Pentagon, okay, so I have no idea, but anyway, I was surprised to hear it and thought it was very amusing. So what actually happens to these eigenvalues? What you can show is that lambda nm over m squared, pi squared, limit m goes to infinity. So this is the label of the eigenvalue. This goes to 1. So in other words, these eigenvalues rise as the square of their label. And so they go to infinity. Now here's what's more interesting,
I have a question.
All right, let me just finish the sentence, then I'll go to your question. What's more interesting, I think, is not simply that the eigenvalues go to infinity, but the eigenvalues going to infinity implies that the eigenfunctions are complete. And when you think about quantum mechanics, what you are always talking about is that your eigenfunctions have to be complete because you want to be able to express any system as a linear combination of eigenfunctions. Yes?
So we calculate k and m according to the
Let
boundary
me get
condition.
closer so I can hear exactly what you're saying.
So we calculate the k, n, and m according
As the zeros of the Bessel functions and
what's the value? I mean, how we calculate?
well, that's a British state secret. In other words, you solve the equation Jn of k and m equals 0, and you know what Jn is. Now, the reason why these things were state secrets is that solving this isn't trivial because Jn is not a linear function, it's not even a polynomial, it's an infinite series, and it's not even a simple infinite series. It's a complicated infinite series. So cylindrical Bessel functions are I don't like them as functions, okay? I mean, if I have my choice, I avoid Bessel functions. Yeah.
Do they know who found the zeros for the Bessel?
What?
Which mathematician found the zeros?
Well, I imagine Bessel had a good idea what some of them were.
Okay.
But of course,
in
other words, you know some of the first or second zeros of some of the lowest order Bessel function, J0, J1, J2.
Okay, so the British, they just do like some
the
higher
state
ones.
secrets were getting these eigenvalues exact, and for all values of n and m.
Well, I have a question.
Anyway, as I said, I was not in the British military in the Second World War. Yes.
We have this equation because we have the condition u. We have this equation because we have u0 equals to 0, u1 equals to 0, right?
Well, we have this because we're requiring this.
Yeah. But in the previous case, we don't have this boundary condition. So how we calculate?
This is
lambda?
a boundary condition.
Yeah. In the previous case, we don't have the boundary condition. So how we calculate lambda?
Well, no, we always impose boundary conditions, right?
Okay.
In other words, if you have a solution, well, I mean, after all, remember the domain. Remember we were talking about a self-adjoint differential system. That means that we had a domain and a domain star, and they were the same, and the domain and the domain star were functions that were twice differentiable on the interval, and that made these, let's see, where did we have, I don't know if we even have it on the board. Well, the boundary term, in other words, if you do this thing with a second order differential operator, you get a boundary term that's more complicated here. And in fact, that boundary term, as I recall, is just u p or u prime pv ab equals 0. Okay, where p is the function. And so we require all the functions in the domain to satisfy this. U and v are in the domain. All of them have to satisfy this. So we always had boundary conditions there. And the boundary conditions make the two boundary conditions for a second order differential equation make the solution unique. Okay, so let's see. Right. Okay, so now let's make more contact with quantum mechanics. And so let's look at the Sturm-Liouville. Both of those names are so damn hard to pronounce. In fact, I'm probably mispronouncing both of them, but anyway. So let's talk about regular Sturm-Liouville system, and it's actually a set of regular self-adjoint differential systems that have the same differential operator L, the same interval AB, the same domain D, that those are the functions that satisfy the boundary conditions, and they all satisfy L psi, which is equal to minus P psi prime prime plus Q psi is equal to lambda rho psi. So I'm using psi because I'm thinking about complex functions, because I want to make contact with quantum mechanics. If this were a math class, this would be U or V or some other ordinary letter that doesn't suggest complexity. Lambda is the eigenvalue, and P, Q, and rho are real, continuous. Rho is positive on the interval, but it might vanish here and there, isolated points. Okay, what we have is that, okay, what I wrote down there was too simple. What we actually have is the wronskian of, let us say, psi prime and, I here psi prime and psi star, but it seems to me it is instead psi prime and chi. AB should vanish. Okay, anyway, suitable bound, it's whatever the boundary conditions are when you integrate this thing and do this. In other words, we start with chi L psi, and because it satisfies this differential equation, we're able to say that chi L psi, which is the integral A to B of chi star L psi dx, is equal to the integral AB L on chi star psi dx. And one can think of this as L chi on psi. And if you want to think about this in Dirac notation, you can think of it as chi L psi is, that's the left-hand side. This thing is L chi psi, and L chi psi is psi L chi star, and that is psi L chi star, and that would be chi L dagger psi. But now if you compare this with that, you see L equals L dagger. All right, there are other ways of doing it that might be a little bit shorter, but okay, so let's suppose psi I and psi j satisfy these equations. L psi I is an eigenfunction with eigenvalue lambda I, this weight function rho, that's psi I, and now we have psi j is lambda j rho psi j. And this is regular Sturm-Liouville and so forth. So what we do is we multiply this by psi star j. We take the complex conjugate of this and multiply it by psi I. So we have psi I L psi j star, and that's psi I lambda j star rho psi j star. Okay, now what we do is we integrate the difference of these, and what we have is that, well, we use something. So let me grab an eraser here. So what we use is that integral AB psi j star L psi I dx is equal to the integral AB L psi j star psi I dx. That's because it satisfies the Sturm-Liouville system and so forth, and the functions also satisfy the boundary conditions, so the other term vanishes. This is very much like Lagrange's identity and Green's formula and so forth. That means then that 0 is the integral of psi j star L psi I minus L psi j star psi I. So that's using this. All of that dx AB is then equal to, because this is equal to lambda I psi j star rho psi I, and the other thing is equal to psi I lambda j star rho psi j. And so this whole thing is lambda I minus lambda j star times the integral a to b of psi j star rho psi I dx. And, okay, so the first thing we do is we set I equal to j, and then we get the equation 0 is lambda I star minus lambda j integral ab rho psi I absolute value squared dx. This is positive, and so what is this? This is I. These are both I, because we set I equal to j. So this says lambda I equals lambda I star. The eigenvalues are real. And once the eigenvalues are real, we go back to this equation, and we have 0 equals lambda I minus lambda j times integral psi j star rho psi I dx ab. And so this says that the eigenfunctions are orthogonal when integrated with respect to the weight function if the eigenvalues are different. So this is the standard thing that you've seen in quantum mechanics classes, although I think in quantum mechanics classes the rho shows up as a kind of a mystery guest, and teachers usually teaching quantum mechanics distract you from don't look at rho's. I think. All right. Okay. All right. Well, what we've got here are complex eigenfunctions, and I made things complex because in quantum mechanics things are inevitably complex, because if you have any eigenstate, you multiply it by a complex number, it's still an eigenstate representing the same system. And so this may, if you now look at this, since the lambdas are real, the rhos are real, and L is real, involving P and Q, which are real, what you can do is you can say, not only do we have L psi I equals lambda I rho psi I, but L psi I star equals lambda I rho psi I star. And so now you can subtract, yes. You can subtract, or you can add the two equations together, and then you have the real part satisfies this eigenvalue equation. Subtract to get the imaginary part satisfies the eigenvalue equation. Yes?
Okay. Yeah, you were saying like, oh, in quantum mechanics they're always like, don't look at the rho, but isn't it always the case that rho is equal to 1 in quantum mechanics?
No.
No?
No. Or it's been hidden. I mean,
Sure.
you've changed variables, made it go away or something. I don't know.
Okay. Well, yeah, I'm just thinking like if you start out with time-independent Schrodinger equation, then you always have P equal to 1, Q is your potential, and then your eigenvalue is just the energy times the function again. So wouldn't rho be 1, Q would be 1, Q would be...
If, all right, fine. Suppose you were doing Schrodinger's equation in 3 dimensions, and your problem had cylindrical symmetry. Then, you know, if you turn the cranks and change variables and everything, you have Bessel's function.
Okay.
There's rho.
Sure. Okay.
It's
Sure. I guess I'm just, yeah. If this was...
okay. Now, so this may make it seem that there are 2 eigenfunctions for every eigenvalue: the real part of psi and the imaginary part of psi. On the other hand, all right, let me read the text here to get this completely straight. So the fact is, each eigenfunction, though, satisfies two boundary conditions. It's a second order equation, so it's unique. The eigenfunctions are unique. And in fact, what you can do in all these regular Sturm-Liouville equations is you can take all the eigenfunctions to actually be real. And I remember when I was taking quantum mechanics and Schwinger was teaching it, he mentioned in an offhand way, he said, if it weren't for the spin of the electron being a half, we wouldn't need complex numbers in quantum mechanics. I don't know if he meant that absolutely, but very often the i's we put in and then we cancel them. For example, e to the I px. What is that actually? It's e to the I h bar over I. Well, let's make it p times some constant a. It's a d by dx. The i's go away. So what he meant was that apart from things having to do with fermions, you don't really need complex numbers. And so in other words, all these eigenfunctions can be real. So now you can say, well, what about Wronski's formula? If you have one eigenfunction, you can find one solution, you can find a second. Well, as I just demonstrated over there, you start with L0 and you get Q, and Q blows up at the, Q doesn't satisfy the boundary conditions. All right, so that's a surprising thing. In other words, our use of, there's an overuse of complex numbers in quantum mechanics. I don't know. So what do we actually have then? And let me just sort of summarize. Well, we're basically out of time. But what I can summarize is, really quickly, is that if we have any function that's in a vector space of functions that we're talking about, and it may be, let us say, any function in the domain, for example, so it satisfies the boundary conditions, and it's, let us say, square integrable, then we can write this as a sum of ai ui of x, and I goes from 1 to infinity. And on the other hand, what's meant here is that the limit of the integral ab of the absolute value of f of x minus this sum up to n of ai ui of x, absolute value squared rho of x dx, goes to 0 as n goes to infinity. So this is called convergence in the mean. And these functions f here, they don't need to be in the domain. All they need to be is square integrable. And as I mentioned to you earlier, weeks ago, the best way to think about integration is the way that we never get taught, namely Lebesgue integration. If you think in terms of Lebesgue integration, one can prove all these theorems in a way in which they're much more general than in the case of the traditional traditional integration. And these eigenfunctions are, of course, are orthogonal. Ui rho uj dx is 0. They're real, so I left out the star. And these eigenfunctions, lambda n, go to infinity as n goes to infinity. So the divergence of the eigenvalues is related to the completeness of the eigenfunctions. And I think that's interesting. Okay, we can turn the thing off.